This question is about diffraction gratings. Moana is doing an experiment in the laboratory and she shines a laser beam at a double slit. And she observes an interference pattern on a screen. The diagram below shows the experiment. Moana measures the distance between adjacent bright spots and finds they are 0.0100 meters apart. So that's x, the distance between the bright spots. The slits are 1.28 times 10 to the minus 4 meters apart. That's little d. And the screen is 2.10 meters from the slits. So we call that big L. Okay, show that the wavelength of the laser light is 6.10 times 10 to the minus 7 meters. Alright, so to do this, we go n lambda equals dx over L. In fact, we can ignore the n there. Lambda equals dx over L is equal to 1.28 times 10 to the minus 4 times 0.01 divided by, and big L was 2.10. So what did we have again? We had 1.28 times 0.01 divided by 2.10, which gives us 6.095 or 6.10 times 10 to the minus 7. Let's write the unrounded one because this was a show question. 6.0952 times 10 to the minus 7, which is approximately equal to 6.10 times 10 to the minus 7 meters. Right. Next question. Moana replaces the double slit with a diffraction grating in the same position. The diffraction grating has 500 lines per millimeter, so that's n. Calculate the angle between the central antinodal line and the first antinodal line. Okay, so that's the angle between the 0th and the first. So that's just going to be lambda equals d sine theta. So theta is equal to the inverse sine of lambda over d. But we don't know d. We need to use this 500 lines per millimeter to find d. So d is equal to 1 over n, which is equal to, if there are 500 lines per millimeter, there are 500,000 lines per meter. So that's 1 over 500,000. Oh, in fact, I'll do this on a new line, which is equal to I should be able to do that in my head really, but it's 2 times 10 to the minus 6 meters. Okay, so then theta is going to be equal to the inverse sine of lambda was 6.10 times 10 to the minus 7. We'll use their value rather than the unrounded one, over 2 times 10 to the minus 6, which gives us 6.10 e minus 7 divided by 2 times 10 to the minus 6 gives us 0.305, and then we want to take the inverse sine of that. Oops, I just pressed an equal sign too many. Let's just try that again. So we'll go 6.1 times 10 to the minus 7 divided by 2 times 10 to the minus 6, close bracket, inverse sine 17.758 or 17.8 degrees. All right, this is our final answer. Explain what would happen to the distance between the bright spots on the screen if the laser source is changed to one with a shorter wavelength. Okay, so we can say theta is equal to the inverse sine of lambda over d. So if lambda decreases, theta also decreases. This means that the spots, what are they called? The bright spots, will be closer together. Okay. I suppose we could say in terms of path difference. So maybe let's just do that as well, just to hedge our bets a little bit. So note, smaller lambda means path difference needed for an antinode will be smaller, because the path difference has to be a whole number of wavelengths. So angle decreases. Okay. I suspect that our first answer is okay, where we use the equation, but perhaps they wanted something about path difference, so I'll just add that in. Moana then shines white light through the diffraction grating. The pattern she sees is shown below. So we get this one. If you're looking at a printed black and white version, you might not be able to see it very well, but you can always look at the online one as well. Explain the pattern Moana observes. Your explanation should include why the center is white and why there is a colored spectrum on each side, and why there are dark regions between the white and colored regions. Okay, so at the center, all wavelengths have a maximum. And all colors combined make white. Maybe we should say also, note, path difference for central antinode is 0 times lambda for all wavelengths, which is 0 for all wavelengths. Well, let's just say 0 times lambda. Okay, and then why is there a colored spectrum on each side? First maximum is given by lambda equals d sine theta so angle will be smallest for blue, or for short wavelength, which is violet or blue, and increase with wavelength, resulting in the observed colored spectrum. Okay, why are there darker regions between the white and colored regions? Between the maxima, all wavelengths have minima. With this number of slits, there will be very many minima between the maxima. That's another word for nodes and antinodes. Be very many minima or nodes between the maxima or antinodes. Making the region effectively dark. Oh, well, for all wavelengths. Making the region dark. Okay. Cool. I feel like we fully answered that now. Okay, that last point is kind of tricky. It's probably enough to say that between the maxima, there are minima or regions of destructive interference. So we can say these are regions of destructive interference. Okay, so we'll end there. You can have a look at the mark scheme for that question. They may have a slightly different answer, but that's sort of effectively what you would need to say. And presumably that's an excellence question given the number of lines we're given.